afternoon, everybody. The Earth says hello. Welcome to Nanyang Technological University's virtual open house for the School of Physical and Mathematical Sciences, also known as SPMS. Woo! My name is MJ. I'm the co-founder of a science channel called Just Keep Thinking, and I'll be the MC for today. We are currently with the Physics and Applied Physics Division, also known as PAP. Woo! All right, just to clarify that we are in no way involved in politics despite sounding so. And currently it's my third round of emceeing. I'm still very excited. My particles are at a higher energy level state. So hopefully we will be able to give you an informative and mildly entertaining session for the next 1 hour. So for all of you guys who are tuning in right now, you must be something of a physicist yourself. So I'm going to ask you a very simple physics question, all right? Do you know why physicists never wear black socks? Because they're afraid of creating black holes in the socks. You get it? Okay. Understand? Okay. Jokes aside, let's get down to business. Starting off with the first speaker of the day, Associate Professor Albert Chia, who will be giving a welcome address and also share more about PAP's undergraduate programs and curriculum. Also, if you have any questions throughout the session, please do your questions through the Slido app for our Q&A segment later on, or you may do your questions via PAP's Telegram channel at NTU_physics. So without further ado, let's get the ball rolling by inviting Prof. Chia.
Hi, good afternoon. I'm Albert Chia. So in the next 15 minutes, I will talk about what we do here in physics and what kind of education our undergraduates experience. So as some of you know, the future of computing is now the quantum computer, and the future of AI is hardware neural networks. In fact, the Tesla's neural processor in the FSD chip, where FSD stands for Full Self-Driving Computer, is already in production a few years ago. The future of augmented reality in retinal projectors, and it all starts with physics. We have to know the what happens at the microscopic level, what happens to these materials, what happens to the electrons, before we can even think about making them for everyday use. So basically, the study of physics is a study of the laws of nature in that broader sense, how to study them and how to apply them. And our students are exposed to so-called the 4 pillars of physics: mechanics and relativity in year 1 and 2, electromagnetism in year 1 and 2 as well, quantum mechanics in year 2 and 3, and thermodynamics and statistical physics in year 2 and 3. So a lot of people have the misconception that physics is just theory, but it is not. It is a mix of theory, experiment, and computation. In fact, a lot of physics research is a collaboration between theorists and experimentalists. And we are called physics and applied physics because we offer fields in fundamental or pure physics, for example, condensed matter physics, or physics of information, or atomic physics, or electrodynamics. But we also have branches of physics that are more applied in nature, for example, biophysics, nanoelectronics, and photonics. So in year 3 and 4, we offer more advanced courses aimed at furthering the understanding or exploring the applications of physics. Our students also get to work on cutting-edge research in the professors' labs, and we have professors working in all different fields of physics, as shown in this slide. We have state-of-the-art facilities for teaching and research. The figure at the top right-hand corner is a dilution refrigerator that can cool things down to millikelvin. And the co-atom lab at the bottom left corner makes use of a dilution fridge, but using the process of laser cooling, they could cool atoms down to nanokelvin. So that's really, really cold. At the bottom right-hand corner, you have the STM lab, the scanning tunneling microscope, which can look at atoms on the surfaces of materials And there's also an ARPUS, which is an angle resolved photo emission spectroscopy. We teach many different things in physics. There's a strong emphasis on mathematics. There's a strong emphasis on data analysis as well as programming. But the ultimate goal is to advance the fundamental understanding of the different fields of physics. So our graduates are very versatile. So this is our NTU physics program. On the left-hand side, you can see there's a double major in mathematical sciences. And on the right-hand side, there are 3 second majors, one in microelectronics engineering, one in medical physics, and one in data analytics. So our students in year 1 and 2 are put through the fundamental understandings of the key theories in physics. And when they go to year 3, they branch off to either pure physics or applied physics, doing the different concentrations. Our students go for cool exchange programs in overseas university like Beijing University, Australian National University, Cambridge, Harvard, UC, Berkeley, and so on. And the most common question that applicants ask me is, where do our physics graduates end up? So our physics graduates do all kinds of things, from PhD to scientific research to engineering to non-engineering jobs like management or software development. They also work in government sectors and others. So for those of you who are interested to do a PhD after your undergraduate physics degree, these are the universities that our graduates end up in to do their PhDs. The very top universities in the US, the UK, and as well as locally. We also have graduates working for research institutes like A-STAR, National Cancer Center, DSO, DSTA, and Temasek Labs. We also have graduates working in STEM-related industries. The top row are names of semiconductor companies. We also have graduates working in a solar cell company called Solar Frontier, optics companies like Lighthouse, and physics in instruments. We also have an alumni working in virtual reality in Facebook and Google. We also have graduates working in data science and non-STEM industries. For example, Wolfram is a scientific computing company in Illinois, USA. We have graduates working in financial modeling in Hartford and SoCal. We have graduates working in banks. We have a graduate who used to work in Agoda, where he's trying to find out why customers like to cancel their hotel and airline bookings last minute. And then he moved on to Grab, but recently I heard he moved on to a startup company as a CTO called The Joyful Person, which is a very interesting company. Tessian is an email security company, and Tableau is a data visualization company. We also have graduates working in the Ministry of Education as teachers and in the MOE HQ. And these are some examples of our physics graduates, whether working in A-STAR or British Petroleum, or in NTU or in startup companies. So the middle guy on the right, Daryl Tay, he's the guy who used to work in Agoda, Grab, and he's now in The Joyful Person. Chai Shan at the bottom, she's working as a data scientist in Tessian in the UK. About 5 years ago, 5 of our graduates got this cybersecurity job in DSTA. And if you read this article, Jin Yi said that the rigorous training in theory and experiment enabled him to get this job. So we are very proud of them. So from these few slides, you can see the various kinds of paths that our students take after their graduation. This is the end of my talk. If you have any more questions, please go to Slido and enter the code 616230. Thank you.
Thank you, Prof. Shah, for the rather insightful sharing of what PAP is all about. Next up, we have Mr. Brian Cheng, who will share more about his academic journey and research journey as a PAP student. So, whenever you're ready, Brian, you may begin.
Good afternoon, everyone. My name is Brian, and I'm a Year 3 physics student. So let me begin with my academic journey from my freshman year. In the very first week, I met my academic mentor. Everyone in NTU will be assigned one. You have a choice between lifestyle, industry, and research mentors. And I chose a research mentor, and Prof. Sam was assigned to me. And in the very first week, I didn't really know what to expect. I asked him a very simple question. Oh no, so what do you do, right? So then he asked me how much time I had. And then we gradually proceeded to spend the next hour in his labs, then him trying to explain to me what this lab does, or what this equipment does, and what he did in his labs. So he's an experimentalist. And so I'd say that the main difference between, let's say, JC level and uni level physics is that there's the addition of labs. And so these are some of the images that I've taken from my undergraduate lab, where we did some sodium doublet experiment from the atomic spectra. And it is a bit different in the sense like you need to be able to find out slightly deeper physics by yourself. So in that sense, I had to ask some of my professors, what is actually going on, because a simple explanation that they explain to you is not really going to cover all of the deep physics. And so that begins my research journey, and I will be highlighting some research programs that are unique to SPMS specifically. So there's the Odyssey program, and this is a paid research program that I undertook when I was at the end of year 1. And so yeah, you can start really early. There's no you must be year 2, you must be year 3 to start this. No, I started it straight in year 1, and I did experimental physics. And here's an image of my postdoc. He's filling up liquid nitrogen, and it's literally a very cool image. And along this summer research, right, it's a very short 3-month program, and you get to learn things that you would not be able to, and actually try your hands on research at the first time. And I also won an award, and then there's some cash prize as well. And so some of the other research programs that are unique to NTU, right, is this Eureka, which stands for Undergraduate Research on Campus. And this is a 1-year research program, and this is an opportunity to conduct research in a very structured program. And unfortunately, this is by invitation only, so the university invites you to join in with this Eureka program. And the Eureka experience is quite interesting. So like I said, it's a very structured program. There's workshops, and there's online courses on scientific integrity. There's a poster presentation. There's a report that you have to submit at the end. And there's some subsidies, financial subsidies for the project, as well as if you are, let's say you are really, really outstanding, you can publish some results by the end of it. You have first author or second author, I think, on some conference or some journals. There's a conference subsidy up to $2,500 so that you can, even now, you could take a VTL to another country and attend their conference in person. So in summary, NTU offers additional research opportunities for undergraduates that are not available for some of the other universities. For me, the short projects like Odyssey, they allow you to take a risk to see what you like and dislike, because especially when you're year 1, year 2, you do not actually know what aspects of physics do you like or dislike, like experimental or theoretical and more simulation based. So like just last summer, I took some a more theoretical and more coding-based project. So previously I had only been doing experimental physics. So it's only a 3 months project. So if you do not like it, you can stop it after 3 months, right? There's not a long-term commitment. And longer projects like Eureka allow you to fully integrate into a scientific group. You can learn skills such as literature review, or you can experimental skills and deepen your understanding of theory. And then some of the results that I have achieved in my 1 year in Eureka. So but in the end, research is a process that you should also have fun with. So in the first 3 months, I kept pestering my postdoc. Because I found out that my lab had liquid nitrogen, right? So I kept pestering him. Oh, can I make liquid nitrogen ice cream? And at the end of it, I did make liquid nitrogen ice cream, as you can see. And so yeah, just try to have as much fun as possible in your research as well if you do select that path. And if there's any questions, you can go to Slido.com and enter the following code. And I would like to pass the time back to the MC.
All right. Thank you, Brian, for sharing your academic experience and your life experience here as a PAP student. They all sound like a proton, very positive, and I hope it will be the same for you guys out there as well. So just a reminder to send in any of your questions via Slido for our Q&A segment later on, and you may also ask them via PAP's Telegram chat at NTU_physics. Next up, we have Mr. Tong Jia Rui, who is a SPMS alumni that graduated in 2019. So not only will he be providing some of his learning experience, he will also be giving some of his internship and graduation tips, which I'm sure will be useful to all of you out there. So Jia Rui, whenever you're ready, please take it away.
Okay, thank you, MJ. Okay, thank you everybody for coming to today's open house. I'm Jia Rui. I'll be doing the alumni sharing for today. So I'll share more about my life in SPMS and NTU, and also how SPMS actually developed me both academically and also practically. And at the end, I'll give you some takeaways for you people who are very eager to come in to join us. So a bit of self-introduction. That's me when I was younger, and I think I still look the same. And I graduated before COVID in 2019 with a bachelor in applied physics. So I'm a very normal student. I did my 4 years from August to July, and also from then there's such thing called concentration. So I actually concentrate my studies into semiconductor physics. And for now, for my job, I'm working both as an integration engineer in a company called Global Foundries, and I'm also a NTU PhD student in applied physics. So this is possible due to this program called Industrial Postgrad Program, also known as IPP in short. So this program is actually a collaboration between the company and NTU for the graduate students to experience both the industrial and research life. So what do I do as an integration engineer? Okay, so as an integration engineer in GF, my job is to integrate a technology into circuit levels for commercial use. So I'm actually doing research on something called the resistive RAM, or is known as RE-RAM in short. So you can see picture A. That's the structure of the resistive RAM. It's actually very thin, only 3 layers, can be scaled down to nanometers, and you can. I think you don't understand picture B, but there's actually a graph showing the performance. It's low performance while having such a small structure. So imagine this: if you can make this, compare millions and millions of this into all your daily IoT devices. This will make all your devices consume less energy. That means longer battery life, and also it won't lag as much. Yeah. So my second job as a PhD student, I'm currently in my year 3. And I'm doing my research under the supervision of Prof. Liu. Yeah, he's a handsome gentleman in the middle of the picture, wearing white. So what do I do? My research is actually linked to my role in the company. So I'm doing more towards the research on the science and investigation behind how this RE-RAM work. And from there, I will optimize it and then investigate on the ways to improve it so that they will ensure that the RE-RAM will always have a constant optimum performance. And from there, I'll put it into circuit level by using the integration methods. So that's a bit boring. So I'll move on to my life in SPMS and NTU. So life in SPS and NTU can be very, very well balanced and fun. You can see I joined in non-academic start way. You can there's a wide variety of CCA NTU. Whether you like me, whether you like dance, you can join like a breakers club or any other hip hop club. And also, if you don't like CCAs, you can also attend all the SPMS events like orientation camps, Halloween, a Valentine's Day event, a Chinese New Year event. And for us, especially for physics, we actually have something called a PAP day, where we can come down to the atrium here, like where we are now, and have free gift, free drinks, free food, everything. Yeah. For academic wise, which I believe you can see the bottom two pictures will be most what fill up your handphone, the album. Okay, so there's lots of random lecture notes that you take, tutorial question pictures that you take, where you got no time to take down in time during lessons. So all this academic is actually, I believe, is challenging yet very, very interesting. And apart from the normal curriculum, there's also a physics related competition for you to participate in both locally and overseas. And also from there, you can also, if not, you can also go other overseas university for exchange program, which I believe is opening up after this COVID situation. After that, most people out there will either go internship or FIP or both. I believe now it's both for you to get more experience. So my more fun years are actually in year 3 and year 4. So in year 3, I went exchange in Beijing, and we went. Then during the studies, we also go to what Temple of Heaven, Great Wall of China, just to have fun and experience the life there. And I also did a dance performance during that time. I joined the break dance club, and I did something called a fusion, where all the dancers of all CCA come together and we just put out a performance together. So for year 4, I danced again. I went for the CAC Synergia Ball for all of us to dress up nicely to celebrate the end of the academic year. Then I did my internship at my current company. And finally, I graduated before COVID without wearing masks. So some things I want you all to know, like how SPMS had developed me. Academic-wise, basically we have more physics knowledge, as we are all exposed to different physics fields like quantum mechanics, and yeah. And from during the lesson, actually Prof will actually link all this information, all this knowledge to real life application, and like in my case, it's more towards engineering. And apart from that, SPMS actually invite famous researchers from around the world to give guest lectures. Okay, so some of them can be very, very famous, like Nobel laureates. They are like the J. Cho of the Mendel Pop. Yeah, so they are all very famous, and you can talk to them, ask them questions, and see whether your interest lies in their research. And definitely, there's lots of lab works, so we will need to have you gain better data sorting skills and information processing skills while reading all the information from textbooks and lecture notes. And from there, after you gather everything, most of the time you need to do a presentation or report. So analytical skills will be developed. So other practical development, subconsciously you'll have a better time management as you go on, from year 1, year 2, and year 3, as the workload increases bit by bit. And there will be more and more projects, so you'll need to do a lot of teamwork, work with people from all different fields, walks of life. And from there, from project works, courses, you need to do all your presentations. So almost every courses they'll have presentations. So how to present an idea to professionals or just a general public. And also, I believe you have something called the grit, the perseverance to get through the semester, and which I believe will go on a long way in your career and life. So for those who are very want to prepare from year 1, so here are some of my tips for you. So during your 4 years course, you can find your interest in any specific field during your lessons. For mine is semiconductor physics. And annually there's career fair, career talks by NTU Career Office. You just go there, then talk to the companies, talk to the HR, find out what they are looking for, what criteria they're looking for. After knowing that, what I did, upgrade myself. So you take out more relevant courses either from NTU or from online or from YouTube's. And then you can find a good, very relevant internship for you to get more industry experience and for you to boost up your resume. And lastly, something that is very, very good and value adding is there's also career coach here, which actually will guide you through resume writing, guide you through better interview skills and networking skills when you go for events. So from my sharing, I hope you can have some takeaways. Okay. So university education, like, it can be very, very challenging but can be very fun too. Like what I experienced actually my university is very, very fun. I joined a lot of CCAs, lots of events, went for orientation camp as a freshman, as a senior. Yeah. And something I want to let y'all know is that help is always available in NTU and SPMS as long as you seek it. Yeah. So in SPMS, for ORD NSF, I know you have wearing helmet for the past 2 years. So there's actually preparation classes for you in the future, just before you matriculate. And the syllabus here is actually very, very progressive. They will expect you to do Schrodinger equation, quantum in just year 1, sem 1. The tutors here and the professor are very, very friendly too, and they will take time to have private consultation with you if you got any clarification and that you don't know during the lesson and lectures. And definitely, I believe SPMS has prepared me to be workforce ready for me to do my current 2 jobs and manage my time properly. And in NTU Career Office, there's networking skills, there's pitching skills, teaching you how to network yourself, how to boost your presence in front of professionals. Resume writing, how to catch people's attention within the few seconds when they take out a resume. And interview skills, how you present yourself in front of a panel of HR and your directors. So that's all from me. I hope to see you guys in PAP. And definitely, if you have any questions, just slide in to our Slido at 616-230. Thank you.
Thank you, Tiare, for all of your golden advices to all of your potential juniors out there. Just to reiterate, he's actually a current PhD student, so I'm looking forward to address you as Dr. Tong Tiare next time. But for now, Tiare, you 加油 first, okay?
Yeah, sure.
Next up, we have something really special. It will not be a sharing segment, but it will be a mini lecture by Assistant Professor Yang Po on the quantum Hall effect, condensed matter physics. So I'm really stoked about this because the last time I ever touched physics was in secondary school. So I'm really excited to experience a physics lecture in a university setting. So whenever you're ready, Prof. Yang Po, the stage is all yours.
Sure, thank you for the introduction. Hi everyone, good afternoon. So today I'm going to give you a mini lecture in condensed matter physics on this topic of the quantum Hall effect. So the quantum Hall effect is actually a very interesting, important system in physics, as you can see from this brief history. It was first discovered as the integer quantum Hall effect in 1980, leading to a Nobel Prize in 1985. And 2 years after the discovery of the integer quantum Hall effect, the fractional quantum Hall effect was discovered, leading to another Nobel Prize in 1998. And this is even a more interesting system where we can realize basically particles that looks like a fraction of a single electron. And they can be very useful for the construction, for example, for the quantum computers. And the discovery of the integer and fractional quantum Hall effect also opened up a new chapter in physics in our way of understanding and classifying different types of materials. The so-called theory of topological phases, where phases means different types of materials. And this also led to another Nobel Prize in 2016. Okay, so before I go into the details of quantum Hall physics, let me also first talk a little bit about the condensed matter physics, or one of the largest branch in physics, where we basically try to study the properties of materials, in particular materials consisting of a large number of electrons with charge and spin, and they can strongly interacting with each other. So in our modern day lives, a lot of things we use today are impacted by the advancement in condensed matter physics. For example, for the transistors and diodes we find in our cell phones and computers, the superconductivity, superfluidity, and even topological materials that are very much related to the quantum Hall effect. And this field was founded by Professor Philip Anderson, who unfortunately passed away 2 years ago. And he also wrote a very interesting article called More is Different. The title is here. It's quite readable, actually, so if you're interested, you can go online and search for it, where he explained the special aspects of condensed matter physics when studying a very large number of components interacting with each other. I'm going to talk a little bit about this because basically there are two philosophies in science. The first philosophy or approach in science is what we call reductionism, where we try to divide an object into smaller and smaller pieces, for example, from molecules to atoms to electrons and protons and to quarks. The guiding principle is that if we can understand the behavior of the smallest piece, then we can in principle understand the behavior of larger pieces that are made from these small pieces. So this is the principle of reductionism. And as Prof. Cha mentioned before, there are four major pillars in physics here in college. Three of them, classical mechanics, electrodynamics, and quantum mechanics, are mainly dealing with understanding the behavior of a single particle or a few particles, more or less related to reductionism. The second philosophy in science is what we call emergence, where we try to understand the complex behaviors coming from a large number of components or entities interacting, talking to each other. Okay? And these complex behaviors are as fundamental as the behaviors for single particles, and they're very difficult to be deduced from the sum of individual behaviors. So the fourth area of study in physics, statistical mechanics or thermophysics, are mainly dealing with a large number of particles, and we try to study the emergent physical behaviors coming from such systems. And this is also a very popular field of research nowadays because it is quite related to many aspects of daily life, as you can see from the big circle here on the right. It can even be used to describe social systems or organic systems where you have a lot of organisms or even a lot of people interacting with each other, leading to emergent behaviors that are very interesting. Okay, so on a more intuitive level, for those of people who know how to play chess, you can also try to understand these two approaches in science by looking at the chess piece, right? So when you first look at the chess game, you try to understand the rules governing how each piece moves. For example, how the castle moves or how the knight moves. This is more or less like reductionism, where you try to understand the behaviors of single particle or single piece. But that's not just what chess is about, right? For playing the chess, we're actually looking at a lot of moves involving many, many pieces over a very long period of time. And in addition to understanding the rules of governing each chess piece, we are also trying to understand how to come up with a winning strategy. And this winning strategy can be thought of like an emergent behavior where you have a lot of pieces moving around and interacting with each other, both spatially and also temporally. So you can even think of physics or condensed matter physics as a chess game with Mother Nature, with two components, one trying to understand how each piece works, the other is trying to understand how a winning strategy can be developed. Okay, now let's go back to the quantum Hall physics. So here is a schematic drawing of a Hall bar, where basically what you're looking at is just a bar of metal consisting of electrons, and with a perpendicular B field, the magnetic field going through the Hall bar. So when you inject electrons in one direction, you will see an accumulation of voltage in the perpendicular direction, denoted by those pluses and minuses. So if you look at the electron in this Hall bar, it will experience two forces. One is the Lorentz force coming from the magnetic field, basically coming from the special relativity. The other force is the electrostatic force due to the accumulation of the charge. Right? So these two forces will balance out eventually, leading to this interesting relationship. The Hall coefficient is something that we can measure experimentally due to this condition, and it's equal to the inverse of the charge density. There's a more general way of understanding the Hall physics or quantum Hall physics. So imagine if you're a person in a lab looking at a very large piece of metal with a perpendicular B field through it. So right now we're just looking at a collection of electrons, right? So these are just static electrons not moving at all. But you can always jump into a cart, and this cart is moving at a certain velocity with respect to the metal. Now, from the cart, you see all the electrons are moving. So what you are seeing here is a current. What is interesting is that there is a fundamental symmetry of a universe, so-called Lorentz invariance, discovered by Einstein from special relativity, which dictates that in this moving cart, you'll also be seeing an not only will you be seeing a current due to the motion of the electrons with respect to yourself, you'll also be seeing an electrical field due to the presence of the magnetic field coming from this fundamental symmetry of the universe. Okay, so there is a fixed ratio of the electrical field in one direction and the current in the perpendicular direction, leading back to, again, this Hall coefficient, which gives you the information of the inverse of the charge density. So here is a summary of the mathematical equations governing the physics of quantum, the Hall effect. The main message I want to pass here is also, it doesn't really look very interesting in the sense that if you do a measurement of this Hall bar, the only information you can get seems to be the density of electrons in this piece of metal based on Einstein, based on this fundamental symmetry of the universe, right? But so imagine a surprise when people actually do this measurement. What they see is something that looks like this. So the y-axis is the Hall conductivity, the x-axis is the magnetic field. So based on our argument before, we should be expecting to see a straight line going through with a certain gradient, and this gradient gives you the charge density. But what we actually saw in the experiment are these plateaus forming at very specific locations. And these locations correspond to an integer times a certain fundamental unit. Okay? And these integers are so well quantized, you can't really change them. Normally in physics, when you tune the system a little bit, say by changing the temperature or kick the system a little bit or put a little bit dirt in the system, any value you measure will change a little bit, right? But not the case for these integers. And they're so robust that we can use such a measurement as an international standard in defining the unit of resistance. Now we understand the reason why this is quite robust. It is because, first of all, there's quantum mechanics in here where the ground state has a gap. Second of all, any system we do in experiment has disorder, basically dirt in the system. And it is this disorder that destroys the fundamental symmetry we mentioned just now, the Lorentz invariance, leading to the broadening of these plateaus at integer positions that we can see in the experiment. And lastly is a topology. Such a system has a topological structure. And the integers here are just a measurement of, in some sense, the number of holes in some abstract space. And since it's a number of holes, it doesn't really depend on the shape of the holes, then it has to be integer, and which is why they're so robust. Okay, and this is also why we call it the integer quantum Hall effect. Later on, people discovered that not only will you see these plateaus forming at these integer numbers, they can also form at certain fractional numbers, which is a ratio of two integers. And this is the so-called the fractional quantum Hall effect, coming from not only just electrons interacting with disorders, but also electrons interacting with each other from Coulomb interaction, for example. And such interaction between electrons lead to very interesting emergent behaviors, such as particles carrying a charge that is a fraction of a single electron. And they are the building blocks of the proposal for topological quantum computing due to their topological structures. And since they are very robust, you can kick the system and they don't really change, right? So they are very useful for the storing and processing of quantum information. Okay, this is also the example where emergent behaviors can come from a large number of electrons talking to each other and talking to other components like disorders in the system. Okay, so for the last few minutes, let me just also explain some of the more conceptual part of this quantum Hall effect about how we can classify different phases of matters. A traditional way of classifying different phases of matters are basically dealing with symmetry. So this is a picture of Lev Landau, one of the greatest physicists from the Soviet Union, who proposes paradigms that we can classify matters based on the symmetry of matters. For example, we know solids and liquids and gas are different phases of matters because solid is different from liquid in the sense that liquid has translational invariance. It looks the same everywhere, but solids are not the same. For any crystal, it's a regular spacing of lattices, that is the positions of these atoms in the solid. So they, in some sense, break the symmetry of the space, which is why we can classify them as two different phases of matters, and they can have very different behaviors. Another example, so this is the case where the translational symmetry is broken. Another example is a magnet. We all have played with magnets before. A magnet is where is a material where all the components or the atoms in the magnet are aligned in a certain position, pointing at a certain direction. We call them spins. So when you're pointing at a certain direction, you are breaking the symmetry of the direction, right? A certain direction is favored. For a non-magnetic system, all atoms are pointing at random directions. So in this case, it has a higher symmetry because different directions are equal, right? So the classification of magnets and non-magnets are coming from the breaking of this so-called Z2 symmetry, that is symmetry between up and down, basically. Okay. A more abstract system is called superconductivity, where the superconductivity and non-superconductivity is coming from the breaking of the so-called symmetry, U1 symmetry, about the conservation of number of particles, which are not going into the details here. So these are examples that we knew before, where we use symmetry to classify different phases of matters. But now we understand that in addition to symmetry, even for systems with the same symmetry, they can have fundamentally different physics. Like the one you see here with different integer filling factors, or different integer plateaus. Each integer indicates a different phase of matter, and they can have different properties. And these integers are really corresponding to the number of holes in some abstract space, as you can see from here. And different number of holes indicate different phases of matters. It doesn't really matter what the shape of holes are, we're only counting the numbers here in our physical measurement. Okay, so this is a very, very brief overview of a much bigger story, and this is actually my last slide here. I hope you enjoy it, and if you have any questions, feel free to ask me later on. Thank you very much.
All right. Thank you, Prof. Yang Po, for that really fascinating lecture. Now, we shall move on to our Q&A segment. We will answer some of your burning questions. All right, let's see. How many questions do we have? Hold on. Ooh, oh, wow, there's 20. Okay. We'll try our best to answer them all. Let's start off with the first question. What's the difference between physics and applied physics? Oh, well, that's a really broad question. Prof. Chia, would you like to just give a brief answer?
So there's actually a lot of overlap between them, but to a very general answer would be physics would be more aiming at the fundamental understanding of materials and phenomena, whereas applied physics is then to ask, okay, I see these phenomena, I see these underlying theories, what can I make out of it in everyday life? Can I make a transistor out of it? Can I make a better photo detector? Can I can I make a better molecule to manifest a certain functionality? So that is a very brief answer.
Yeah, sure. Go ahead.
Just to add on, when you first join in year 1, it will be the same. Everybody will be taking the same courses, but in year 2 and year 3, that's where you kind of choose your like 2 different branches, right? You either pick physics or you pick applied physics, and some of the modules that you take are a little bit different. So, for example, applied physics has 1 more lab module, and physics has more theory modules as well. Yeah.
All right. Thank you. Oh, please add on.
Yeah, just try to explain this for a more conceptual point of view. I was making this analogy about playing chess and physics, right? So for physics, sometimes we are really focused on how to understand the chess itself and how to come up with theories about the winning strategy, etc. For those of you who play chess, you know there are also people in chess who are writing books about this, right? But it doesn't really mean we are very good players of chess. So when you're doing applied physics, you're really trying to actually learn from these theories in physics and try to be a very good chess player, which is not something that the pure theory people can do. So that's one way of understanding the difference between physics and applied physics.
That's a great point. Thank you so much, Professor Yang Po. All right, let's have our next question.
Take the next 2.
All right.
First 2.
Okay. Must I have taken chemistry in JC to study NTU physics because my subject combination has further math instead of chemistry?
Okay.
Prof. Chia?
This is a very easy question to answer. The answer is no.
N-O.
And O. Okay, as long as
No.
you study H2 physics, you are fine. The next question is also quite easy. Will I have a better chance of being admitted if I took H3 physics in JC? So partially it depends on your U score, but of course when we look at your A-level results, we also will take into consideration the fact that you took H3 physics, and that will be to your advantage as well.
All right. Hope that answers your question. We shall move on to the next question. What career opportunities are there for graduates? It was mentioned in the lecture early on in Prof. Chia's slides, but okay, perhaps you can just give a short review.
Okay, so just now in my talk, I said that our graduates, if you want to do a PhD, our graduates have gone into that field. If you want to do research and development in industry, in national labs like A-Star, our graduates have gone there. You want to do STEM industry, our graduates have gone there. You want to do non-STEM data science, our graduates have gone there also. So our physics graduates are very versatile, like I mentioned earlier, and the training that we give them enables them to go into any field that you can think of.
All right. Thank you, Prof. Chia.
Anyone want to add
Anyone
this?
wants to add on?
No?
You can be a professor. Okay, next question. As a prospective student, can I consider reading quantum physics and linear algebra in the first semester once I join physics? Is this a question anyone would like to take?
Yeah, so maybe
Okay.
I can take this question. So linear algebra is actually taught in the second, it's not taught in the first semester, but it's taught in the first year. So it will be the second semester. And I do believe that it is possible for some students who are a little bit more advanced to try and take on quantum physics. I actually had some friends who did the Odyssey program, and they actually, in the 3 months that they studied under a theories here, and they studied purely quantum mechanics, right? So it is possible, but it would be something that is a little bit more challenging, but maybe to each his own, right? You might find it easier, yeah.
So quantum physics in PAP is a progression as well. We have a quantum physics course in year 1. We have a quantum mechanics 1 in year 2, quantum mechanics 2 in year 3, and quantum mechanics 3 in year 4. So the answer to your question is yes, you can. Our year 1 students do study quantum physics in the year 1 course, and it's called PH1107.
All right. Thank you, Brian and Prof. Chia. Let's move on to our next questions. Oh, the questions just keep coming in. If I join physics, can I read chemistry modules such that the AUs are equivalent to a typical second major in chemistry? So something with regards to the curriculum. Prof. Chia, would you like to take it?
We do not have a Bachelor of Physics with second major in chemistry, but you can. There are certain AUs where the university allows you to take any course from any school in NTU. So you can use those AUs to take the chemistry courses, but I don't think the number of AUs is equivalent to a second major in chemistry. Yeah.
Just to add on, if you are looking for like officiating it, there's actually a minor in chemistry as well. So you should probably look up on the website for a minor in chemistry. That might be possible. Yeah.
All right. Thank you. I hope that answers your question as well. Okay, next question. What can I expect if I read second major in medical physics?
Okay, I'll take this question again. So our second major in medical physics is a brand new second major. So it is in conjunction, as you can see from the board behind me. It is in collaboration with the Lee Kong Chian Medical School, as well as the School of Biological Sciences. So you will learn the applications of course, the first few years, the basic physics, it will be the same as everyone else, and then you will learn the applications of physics in the various medical fields like imaging or proton therapy, and you will also be taking courses from biology and from the medical school as well as being attached to different companies and hospitals.
All right. Thank you, Prof. Chia. Let's move on to our next question. Oh, this is a long one. I recently heard from my seniors in NTU physics that the curriculum is slower as compared to that in other schools. Just to bust the myth, if I join physics, how will the standard curriculum benefit me? Can I skip some modules based on what I learned online, unlike some of the regular physics modules?
So yeah, I just want to add on. So I think like I shared during my talk, NTU really offers, especially here in SPMS, they really offer more research opportunities as compared to NUS. I'm unable to find research as a paid or such a structured program such as Eureka. I would be surprised to find out. But as to whether it is slower compared to NUS, you can also decide to finish faster. So for example, I am actually finishing within 3.5 years. Apparently there are some students that finish in 3 years. God knows how they did it. But if you find the curriculum a bit slower, you could say finish in 3.5 years. Yeah. Yeah.
All right. Thank you, Brian. Hope that answers your question. Next one. Can a physics major specialize in material science during my undergraduate years? Does the same go to environmental science too?
There's a very strong overlap between physics and material science. I mean, for example, if I use lasers to shoot a laser at a material, and then from there I find out what the electrons are doing. I find out how many electrons there are. I find out how fast the electrons move. So is that physics or material science? So it turns out that it is both, right? So a lot of our physics profs do research, which you can also broadly categorize as material science. A lot of the physics profs also collaborate with the profs in material science. And similarly for undergrads, you can do a project under a prof in physics and co-supervised by a prof in material science. So I think the short answer to your question is yes. You will learn a lot of material science if you want to in undergraduate physics.
All right. Thank you, Prof. Chia. Moving on to our next question. Is it okay to join if my diploma is under the relevant diploma, but my diploma did not touch on physics?
Let me just add to that. So some of my friends right now who are studying physics did not actually do their diploma that is relevant to physics. But then, because they are so hardworking, right, and they approach the prof, they try to find friends who are so-called more better at physics, they can actually still finish with or relatively close to first class grade. So that is extremely it also depends on your determination, your grit, not just whether you started off with physics at A-levels or diploma. It might be harder in the first few semesters, but I think actually everyone kind of levels out, towards the end.
So in one of the slides where I said 5 of our PAP grads joined DSTA in cyber security, one of them actually got her diploma in business in a poly. So I teach year 1 mechanics. So the first lesson, she came down at the end of the lecture, she came down and said, "Prof, actually my diploma is in business, how. So I did talk to her. I said, the important thing is your attitude, and the important thing is that you work hard. And now she's doing a very I would say physics and math intensive job in cyber security, and she's doing well. So it is definitely possible for you to do very well, even if your diploma is not related to physics.
Wow, that is really inspiring. Thank you, Prof. Chia, for the answer. All right, moving on to our next question. As an aspiring physics student, can I choose to switch to mathematical sciences to catch up with my friends who are majoring in math, and at the same time continue with my physics mods towards acquiring a full equivalent of a physics major? That's a very...
Yeah, so I'm not sure what you mean by choose to switch to mathematical sciences. So do you mean switch to math as in like a full switch majors, or do you mean like meet people in the school, right? So if you definitely want to catch up with your friends, you can do that in SPMS itself. So SPMS has both chemistry, math, and physics all in the same building, right? And you do see people with double majors in both physics and math, and they do collaborate with each other. Yeah.
So we have a double major, as I mentioned in the slide, in physics and mathematical sciences. So the workload in that double major program is really, really heavy. So if you're interested in both physics and math, definitely I would encourage you to apply for this PHMS double major.
All right. Hope that answers your question, whoever who asked it. Moving on to our next question. I'm looking to join NTU Physics in 2024. Is it possible for me to read courses during my NS days so that I can skip mechanics, optics, and electromagnetics by the time I enter year one? I think the answer is no, but
I don't think it's possible. But you can, like I said, you can definitely do more modules if you're that confident, and you can try and finish faster in 3.5 years or even 3 years, like some people have done.
yeah, but you have to just focus on your NS first, okay? Moving on to our next question. Anyone would like to add on? Oh, no, right? His answer is sufficient. Right? Yeah, no. Just do your NS first. How does participating in compulsory physics lab modules open me up to more research opportunities as a student?
Okay, let me take this. So, first off, I did the physics lab modules, and if you were around for my sharing, I actually first approached my professor about the lab experiment and the lab modules, because the lab modules have gaps, right? They don't truly show what is going on. And so if you are that diligent to want to find out what is going on, you have to try and approach the professors and try and understand what is going on. And when you ask them, then they are like, oh, you're so how do you say, diligent, you're passionate, why not you try and a similar project that I'm doing, in one of his research labs. So that's actually how I started. It's just very basic in year one, something about LEDs, and I transitioned into similar light emitting materials, light emitting devices, and I think that's excellent research opportunities that NTU gives us. Yeah.
All right, thank you, Brian. And it's compulsory, so you have to take it. Moving on, I think, that's our last question for this segment. If you guys are still wants your question to be answered, please do send it in to the PAP's Telegram chat at NTU_physics. So unfortunately, just like some of your relationships, all good things must come to an end unless you have a relationship with Newton's first law here at PAP. So once it's in motion, you just go on and on forever. That is all we have for today's SPMS PAP's virtual open house. Once again, if you have any more queries, do send it to PAP's Telegram chat at NTU_physics. Also, do check out our SPMS tours available for limited signups only on NTU's open house website. These are guided in-person tours that will bring you around the common areas, the teaching facilities, and the laboratories, accompanied by friendly SPMS student ambassadors so that you can have a taste of what your future university life may be like. So some of the slots are already fully booked. Hence, please head to the website, fastest fingers first. Thank you all so much for joining us this afternoon. I hope you guys enjoyed this session as much as I did. Bye!